go into the RRC, this picture kind of tells us the entire thing that we have studied so far, and what exactly would happen when it comes to the L2 and L1 part. So all the L2, L1 layers together, what are they achieving? And we already know that RRC is a kind of a layer that's kind of working towards configuring this L2 and L1, making them work. That is the primary duty of RRC. So I will first explain this picture. This kind of gives you a overall idea of the entire activity we have studied. And from there, it will become easy for us to go into the RRC, because RRC have to deal with this mechanism, these lower layer mechanisms itself. So if you observe here, we have three subunits that are represented on the top: AT, MMI, NAS, and RRC. Uh, Three layers that you see here. What is this AT MMI? Typically represents, AT stands for attention commands, or MMI stands for man-machine interface commands. It is a kind of a way that a human being can interact with the mobile equipment's protocol software. The only protocol software that the mobile your human can interact with is the NAS layer, and to do the NAS configuration a little bit. Uh, what kind of a configuration can be done, etc. We will hit up on that when we are going to go through the NAS layer. But I kind of wanted to keep it here so that you will understand that there is some human interaction that is possible between between the mobile device and people who are using it. So that that interaction is done with this AT and MMI software. Now, uh, this part we know that is signaling. This NAS plus RRC is the signaling block for us. Similarly, on the right hand side, you see there are several applications, 1 to n number of applications, and each one of which is generating the data PDUs. And these data PDUs are typically the IP packets that are originated from several applications. They can be n number of them. And uh, till that part, uh, till that part is the higher layer, which we call it as L3. So L3, either we will have signaling L3 part or user data L3 part. So user data L3 part is these data PDUs and generated by applications. Now this bottom whole thing is representing L2 and L1. L2 we have four sublayers: SDAP, PDCP, RLC, and MAC. And L1 we have only physical thing. Now how I have designed this whole thing here that you are seeing. If you take any particular protocol sublayer, on the left hand side you will have the transmitting parts. So on the left hand side you have transmitting operations, and on the right hand side you have reception operations. So that is how we have I have designed this picture. So that is applicable at every sublayer, even in the PDCP level also. This is the transmitting part of the PDCP. This is the reception part of the PDCP. So this is the transmission. This is the reception. Transmission, reception, transmission, and reception. So multiple PDCPs basically represent, there are multiple operational PDCPs that are present here. So same rules are applicable for the bottom part also. We have the uh, RLC entities, AMRLC, AMRLC, AMRLC. But if you take a look at AMRLC, it kind of contains extra things. So like you have RLC control mechanism to take care of retransmission. So you have these retransmission buffer related mechanisms that is applicable only for AMRLC part. So that's there are here. One question: is the text that is present here appearing for you? Can you read through the text?
Yes, sir.
Okay, that's great. Uh, Now, when it comes to the MAC layer, we don't have multiple instances of MAC layer. So there is going to be a single instance. So again, the left-hand side part is representing the transmission operation, and the Right hand side part is kind of representing the receiving operation on when you are receiving. Sorry for that. Okay, next. Physical layer, the same process. So this particular part that is appearing here is representing the uplink, and this is receiving in downlink direction. So this part is, sorry, so this part is downlink, as you can observe what mobile is receiving. And please remember, I have arranged this whole thing from the mobile perspective, not from the Genode views perspective. Of course, you can reverse it and do kind of consider it as Genode view also. But if you take it as Genode B, in that we don't have the NAS present or AT or MMA commands present. We have only RRC, and also we don't have applications in the Genode B, as the data simply gets forwarded to UPF, or data would be received from the UPF. So Genode B won't be generating the data, because I have considered NAS and data to be shown here. So definitely this picture is a mobile equipment software representation, and their individual sublayers and what are their duties. Okay, so now we'll kind of go dig deep into the details of whatever that we have studied so far. Um, so for this particular situation, we are already considering mobile equipment is in connected state. As you can see on the right hand side, a NRUE who is in connected state. So RRC configuration is kind of working, and all the lower layers have already been configured, eh, and these many lower layers are operating. And please remember, this is just an example. This is not the final setup, or this is the only setup that is possible. Uh, this is one of many possibilities that you may have in a real environment when a real mobile equipment is operating in the 5G NR situation. Now, how many SDAPs I am taking here is only one. If I am taking only one SDAP from the rules that we have learned earlier, so this whole box is only one SDAP. We have only one SDAP for one PDU session. So you have to understand that all these applications are dumping the data or sending the data into the application servers which are located in the same data network. So that is the literal meaning of it. Because I did not consider another SDAP here, so you can take it for granted that I am explaining you the concept related to a single PDU session. It is not associated with multiple PDU sessions. And what is the representation of SDAP only covering these two PDCP boxes? The meaning is SDAP is only taking the data part. It is SDAP is not kind of functional for the signaling section. So if you to take a look at the RRC part, whatever the data that is coming in from RRC, SDAP has got no role to play in that. So that is why the SDAP entity is not spreading into the control plane L3 part. Under the control plane L3, we don't have SDAP. Only for user plane section. Only it is dealing with the data PDUs. So what does it do on the sending side? So we take it from the sending and receiving point of view. We take everything from sending and receiving perspective. So this is how it works out. Okay, now on the sending side, several data PDUs generated from several applications do come in into SDAP. SDAP will identify first the data belongs to which QoS flow by applying the quality of service filters, or your we have learned them QoS rules. We have learned it as by applying those QoS rules. First, it will convert it to QoS flows. Then it will have to map the QoS flows onto DRBs. Of course, you have to ignore this MRB side link DRB part. That is that we did not study. We can ignore them for time being. So it will have to map. First, it will divide the IP packets that are arriving. So each one is IP packet carrying the data. That kind of divided uh, QoS flows, and QoS flows need to be mapped onto DRB. We learned that in 5G, there is a possibility of mapping multiple QoS flows to DRB. But uh, ultimately, SDAP, after deciding which QoS flight data need to be sent on which DRB, it will add the corresponding details in the header. It will note down the QFI number, your quality of service flow identifier. And after adding the header, the SDAP will either dispatch the traffic to this PDCP entity to this PDCP entity or to this PDCP entity. Please take a look at here. We are looking at the transmitting side of the PDCP entities, not on the receiving side. But because I am explaining you the transmission operation right now from the mobile, I'm explaining the uplink situation in the mobile. So each and every PDCP entity, for example, I took one PDCP to working in AM mode, other one is working in UM mode. The UM or AM mode has to do with the RLC entities AM or UM mode. So they are in relation there. Okay, now PDCP adds the sequence number for which we already learned in order to identify the duplicates, and in case of handovers, this thing will be useful. We learned scenarios and seen some examples related to it. But PDCP adds the sequence numbers for the SDUs that are coming from the higher layer. For every SDU, it will kind of give a number in its own header. Then it starts performing the duties. And you can kind of consider these things happening parallelly in here. So header or uplink data compression will take place at the PDCP software. Now, we can move on this particular path um, uh, further, but meanwhile, I will interrupt this particular picture and I will go here. So there are two more PDCPs which are operational that are working on the bottom of this RRC protocol here to process the signaling messages. So RRC can be utilizing multiple PDCP services, but typically PDCP would be working with AM RLC mode when it comes to signaling. UM is not applicable. It is AM mode. So when RRC gives different types of data, some are prioritized messages and some are low prioritized messages. What is it? I will explain later. Obviously, the data comes from RRC. Also, the signaling messages from L3, they will end up in this transmission buffers. So because we wanted to kind of consider the complete software process parallelly, I have to show you. So even for the RRC messages that are coming in into these PDCP entities created, or we call them as signaling radio bearers, we can kind of consider this as SRB1. You can consider this as SRB2. So we have one message coming in from SRB1 for one message coming in for SRB2. And for them also the numbering would happen. Sequence numbers will be added for the L3 messages when it is packed into PDCP packets. But you can observe the difference between the PDCPs that are working for the user plane and the PDCPs that are working for the control plane or the signaling. One box is deliberately missing. The box that is missing is the data compression box. As I already have explained you, data compression or header compression is a procedure that is applicable only for user plane. It is not applicable for the control plane or signaling messages. That's why that box is not there. That is that I've removed that box there. So if we are assuming that RRC generated kind of two messages. One, it decided to send an SRB1 for some reason. One, it decided to send an SRB2 for some reason. And it is also, processing several data PDUs. Maybe two of them have been taken and one data PDU is sent on to this PDCP. Another data PDU is sent on this PDCP. So you have to imagine there are two SRBs that are functional in the live situation, and there are two DRBs as well. So we can consider this as the DRB1 and DRB2, data radio bearer 1, data radio bearer 2, just for numbering. So in your brain, you have to imagine that all these PDCP entities are kind of performing the job parallelly. There are several, there are different instances of the same software who can run parallelly, working for different purposes. Two PDCP entities working for RRC, two PDCP entities for dealing with the user traffic that is coming in from the SDAP. That's how it is. Now, so the data keep moving downwards. In these cases, signaling case, the compression box are not present. Directly, the data would be sent to integrity protection box, where your MAC-I will be calculated for the integrity protection purposes. But here, in case of data, after the compression, then it goes to the integrity protection box. That is the difference uh, in the operational aspects of these PDCPs. Okay. Yet integrity protection at every layer, at every PDCP software, the MAC-I can be computed, and that MAC-I would be attached to the PDCP part. Then all these messages will be ciphered. So we are going parallelly here. So ciphered everything, converted into some secret format by using the ciphering key. And for each one of them, the PDCPs would add corresponding header by noting down their running sequence numbers, whatever the numbers they are. So whatever the number they decided to use, so that based on it, number need not be equal. Just because I'm showing these procedures are equal, you should not consider that everything is equal. The sequence numbers are equal. It will be dependent on at this live before this particular position situation, how many packets of data they have sent on that particular radio bearer. If you have sent more data on a radio bearer, the number would have been incremented more number of times. If you would have sent less amount of data on that radio bearer, your number would be incremented less number of times. So the sequence number won't be equal in all these PDCPs. They will become unequal. But normally when they start at the starting, just to be when the mobile equipment comes into the active state or RRC connected state, the sequence numbers must be zeros. But typically, when they start with zero. But after that, it will become kind of unequal after some time. So according to whatever the sequence numbers that are going on in the live situation, the corresponding header information would be added up. Now, the routing and duplication part, we kind of ignored because we are not studying the multiple cell scenarios. So we have not, I have not considered that situation here. So you can ignore that box, even if it is present. Routing and duplication. Okay, now individual PDCPs uh, doing their duty is completed. They have whatever they are supposed to do. They have provided the security for the data, added the ciphering and integrity details, and if required, header compression. And whatever the activity they are supposed to do, they did, and they all will submit their data into the RLC's buffers, their respective RLC buffers. And if we are in normal circumstances, if there are 4 PDCPs present, there will be 4 RLCs present as well. So into their corresponding RLC buffers, the data enters. Now, we already have learned the RLC level activities. Immediately after the data arrives, RLC adds the header, even before MAC request for any size. You already add the header and keep it, store it in your buffer. So immediately each RLC will be attaching a sequence number. Uh, AMRLC for every SDU, there will be a sequence number. For UMRLC, at first you don't attach the sequence number. Only if the MAC is asking you to segment it, you have to attach the sequence number. So sequence number need to be attached only during segmentation in but in AM, sequence number will be immediately attached for every SDU that is coming from the higher layer. So each individual RLC, they will start processing those SDUs, add the sequence numbers and store them. After storing them, they kind of internally go, each RLC will go and talk to the MAC layer by using the, you know, uh, what we call it as APIs. So the internal links. So they will talk to MAC and explain how much amount of data is kind of waiting in their buffer. A kind of report would be sent to MAC layer from everyone. We already learned that the operation that works in radio is something called as a pulling operation. It is not a pushing operation, it is a pulling operation. MAC layer need to pull the data from RLCs, not to push. RLCs won't push the data. They will simply report what is the size that is waiting in the buffer. Now, what does the MAC do? Because we are considering this as the UE's MAC layer, UE's MAC layer somehow will have to, implement the scheduling logics. It will have to go and kind of communicate with the GNodeB's MAC layer and get the uplink resources required. And we have studied there are various mechanisms to get the uplink resources. Either you can, if for example, if you are out of sync, if timing advance is not there, you have to start the random access procedure. But if timing advance is within the uh, timing advance and you are in sync, and that too you have the resources available for PUCCH, you can send a scheduling request. Otherwise, if you have enough resources to send a buffer status report, you can create a buffer status report and send the buffer status report. So there are various mechanisms. We have detailedly studied all that in the Mac. So what we are doing right now here is we are going to assume that Mac somehow is going to complete that scheduling aspect. This mobile equipment's MAC layer will go and communicate successfully to the GNodeBee's MAC layer and get the required amount of resources needed for carrying this data. But as I told you earlier multiple times, you may or may not be able to get the resources good enough for sending the entire data that is waiting in your buffer. Typically, that most of the times that is going to be the case. So where you can never send all the data at once. You have to schedule it and send it in an incremental fashion. But Mac, on the basis of the resources acquired, by assuming that it is already acquiring the resources, and the transport block size decisions and so on, based on the MCS values and various other things, by considering everything, it will kind of start performing logical channel prioritization. So it knows how much amount of data is waiting in each AMRLC buffer, where they have already reported it. So Mac starts this process. Now, you have to just imagine, right now, RLC's job is kind of stopped. Every RLC's job is halted. And their buffers, the data come from the higher layers as the header has been added, and it kind of, everybody stopped here. Now Mac is taking up the next step. Mac has got the resources. Mac is doing the logical channel prioritization, deciding from which RLC how much data to be pulled on the basis of the prioritization, bucket size, duration, prioritized bitrate, your guaranteed bitrate, whether it is a guaranteed GBR or NGBR case, various things Mac will take into consideration, and it will prioritize that, and it will decide how much it need to pull from each RLC. So by using again the same API mechanisms that these RLCs have used, Mac layer will go and uh, talk to these RLC entities and tell the RLC entities that, hey, I'm expecting this much amount of data from you. Can you please send me this much amount of data? Now, what does the RLCs do? Whatever the sizes that the Mac has requested, their duty is to send that much amount of size. But if the size is matching to the size that is pending in the buffer, they kind of not required to do segmentation. They simply need to send the data as it is, the um, that block of data, the PDU, whatever you have prepared already with the sequence number, you have to send it as it is to the MAC layer. If MAC requested for the same size, exactly matching to your PDU size, but if that is not the case, you have to perform segmentation of the PDUs, and you have to note down the corresponding information with the help of SI information, scheduling information bits. We have learned that at RLC. So each RLC will take up this duty of performing the segmentation and adding the corresponding details. And of course, I'm not telling you that it is mandatory that everybody does the segmentation. Maybe two RLCs might do segmentation, two RLCs might not do segmentation. Okay, so each one, uh, according to the instructions sent to them by the MAC layer, they're acting upon it, and they does the task. They completes their duties, and they add the corresponding headers. After adding the headers, your RLC PDUs are ready. The RLC PDUs need to be sent to the MAC layer. Everybody prepares one RLC PDU, because we are studying here example of one here for everything. Now, out of them, three guys who are operating in AMRLC mode, three guys are working in AMRLC, one guy is working in UMRLC. These three guys operating in AMRLC, after adding the header, this PDU will be stored into retransmission buffer for the purpose of retransmission in case if you receive a negative acknowledgement from the other side. Those three guys will store it. But UMRLC don't have that retransmission buffer. That guy is now ready to send the PDU, but it is not storing a copy of it for the purpose of retransmission, as it is not involved in retransmissions. Now what happens? So everybody would send the data. And remember, logical channel prioritization already happened. I am bypassing that box. Directly, my arrow is getting into multiplexing block. You have to observe that carefully. Because only after logical channel prioritization, MAC has requested different sizes from these RLCs, depending on what it can send right now, how much data it can send right now from each RLC. Based on that only, they performed the segmentation and adding the corresponding RLC headers. So each one will come to multiplexing box. What is the meaning of multiplexing at MAC layer? MAC will note down from which logical channel how much data arrived with the help of something called as subheaders. We have seen that at MAC layer. It will note down logical channel number because each logical channel is having a number. So it will note down those logical channel numbers and it will kind of pack all of it together and form something called as a transport block. So this multiplexing operation is to perform a transport block, is to prepare a transport block. And that prepared transport block, one copy of it will be stored into the HARC buffer because we have two level of retransmission. Why is that, etc. We have learned already. So one transport block copy would be stored into HARC buffer. And then after that, the transport block would be sent to the physical layer. Now there are no more multiple streams. Now you can observe what is happening. All of them have been combined into one block of data. Now this block of data, the duty of the physical layer is to convert that block of data that is arrived into physical signal, into a radio signal that is transmissible or that can be transmitted. So what does the physical layer do now? It will first do the CRC attachment for the transport block, completes this. And just imagine all of it are sitting inside in one single pack. For this entire thing, we are attaching the CRC, not individual for each individual AMRLC entities or whatever. They have been all been multiplexed. So here, understanding the big picture is important. So the idea of placing everything together here is to clearly make you realize each layer, like what exactly is happening to your data. So just because we have 4 PDCPs, physical layer also will be doing 4 processings. No, it is single. It will have to take that completely single multiplex transport block and perform its duties. So it attaches the CRC. If the transport block size is too big, you wanted to have individual CRCs attached for them because you wanted to find out the errors that happen to each individual block to solve the errors much more effectively in the coding mechanism. So you're attaching individual CRCs. And each block will be separately channel coded. And you perform the rate matching, concatenate this code block, and what will come out here after this operation is your code word. Now, in this example, I'm not considering I'm not trying, I don't have space to fit like multiple antenna scenarios. So I've kind of considered a single antenna scenario here. So what happens for the code word? The code word go through the scrambling process. With the help of your scrambling sequence, you scramble the data, scramble the code word, then convert them into modulation symbols. And the modulation symbols will optionally go through the transform precoding process, depending on the transform precoding is enabled or not. This is an optional block. This may be there, may not be there. I have already told you, this is configured by the higher layer, RRC. Chooses either to enable the transform precoding or not. If you wanted to, uh, uh, if you wanted to have the PAPR to be very less, peak to average power ratio, you configure this transform precoding. Otherwise, you disable this. So if you disable it, it will be direct. It will go to the next step. Otherwise, it will go through this process. Because we are studying uplink, as we are studying this whole process as mobile equipments process in uplink. So a transform precoding would happen. And then those things would be mapped onto resource elements that are available in your resource blocks, whatever that are allocated for you for present time transmission, um, subcarriers and symbol positions, etc., etc. And then you generate the uplink signal, either CP OFDM signal or DFT OFDM signal. If in case we are enabling the transform precoding, it is called as DFT OFDM. If transform precoding is not enabled, it is called as CP OFDM. So depending on the transform precoding box is present or not present, we either we call the signal as either CP OFDM or DFT OFDM signal. Generate the signal, send it out into the antenna. The antenna transmits it and send it to the GNODB. So this is the process that happens on the mobile phone side in its L2 L1 block, L2 layers and L1 layers, while transmitting in the uplink direction. Is it clear? Any question in this uplink part? Have you all understood this overall process? Participate, participate, guys. If you have any questions, ask me, please. Okay, I'll ask you one question. What is this random access control and why this random access control is present in the Mac and why I did not explain you that process as part of this operation? Can anyone answer that? Did you get my question? There is, in the transmitting entity of the MAC layer, there is this random access control mechanism. I did not explain that part. Directly, we have taken the data from each RLC, multiplexed, put it into HARP block and transmitted that. Why we did not study this random access control and why in this process this random access control is not involved? Why I did skip that? What is the reason? I'm asking you what is the reason for that? Anyone? There is one answer that is good because already UE is in RRC connected
Yes,
state.
sir. It will be used when it is in idle mode and trying to connect.
Yeah, exactly. Mobile equipment is already in RRC connected state, so multiple people have answered. Good. So mobile is in RRC connected state. And in RRC connected state, I'm already considering that mobile is in uplink sync and it is kind of getting the radio resources in the DCI mechanism or something like that. So you don't require to use this random access procedure in the present situation that the mobile is in. That is why the state is important here on the right hand side. If it is would have been idle mode or if you would have considered special cases like the ones that we have studied at Mac, like uplink sync is not there or etc., that time definitely we have to start this random access control. It is uplink procedure. Because it is uplink, it is kind of part of our TX block in the MAC layer. Because this is mobile, uh, random access procedure is the duty of the mobile equipment's MAC layer while transmitting. It will select a preamble and it will give that preamble to physical layer, ask the physical layer to convert that preamble into a special Jadov sequence and transmit it. Of course, when you pick up the random access procedure, random access preamble, the procedure is not going to be this. It will be little different. Not all these blocks will be present while generating the uh, 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 PRACH preamble. So that is different procedure. I cannot include everything in this picture in one place. Rahul has asked a question. Please repeat the last point. Where to use CP OFDM, DFT OFDM in physical layer? That I already told you. If transform precoding is enabled, if directly you map the modulation symbols onto resource elements, that is considered as CP OFDM process. But if the modulation symbols will go through transform precoding process, convert them into DFT symbols, and you map those DFT symbols, you place those DFT symbols on the resource elements, that is called as DFT OFDM signal generation. It is dependent on the transform precoding is enabled or disabled. Now, when do you enable transform precoding? When do you disable it? That I have already explained. You have put a question on that in your test also. PAPR related. If you want to utilize less peak to average power ratio value when you want to operate with, network will enable this transform precoding. Otherwise, disable it. It depends on the UE's power headroom report also. There is an internal local linking will be there on the basis of that, when to enable it, when to disable it. If mobile is typically facing power related issues in uplink, because it is the mobile that need to transmit the power in uplink. So in such cases, this would be enabled. Okay. Now we are going to study, this is the uplink mechanism. Now we are going to study the downlink mechanism in this part. So in downlink, where the logic starts from, the logic starts from the radio signal. That means mobile receives the radio signal in downlink. It is from the bottom to top. Uplink, it is from the top to bottom. Uplink, the data need to be prepared by taking from the L3, L2, L1 process need to be done, and it need to be sent out in the form of radio signal. In downlink, mobile would be receiving the radio signal, and mobile need to find what is present inside the radio signal, and it need to extract the information from that radio signal. So in downlink, we don't have this concept of DFT OFDM. A transfer and pre-coding mechanism is not there in downlink. So it is only CP OFDM in downlink. So you receive CP OFDM signal in downlink, radio signal. You only receive your resource elements that are applicable for you, depending on which are reserved for you in downlink operation. And you demodulate those symbols. You extract the digital data out of it. After that, you perform the descrambling. After performing descrambling, you get code word. Now this code word contains coding information and CRCs, etc., etc. So now you have to kind of find out whether this code word is received without any errors or not. Whether you do the CRC validation, you use the code, you apply the decoding operation, or solving the bit errors, if there are any bit errors occurred for this radio signal that you are receiving. So all that will take place in the physical layer level. Once every reverse operation happens, ultimately all the physical layer headers like CRC bits, coded bits, etc., everything will be dropped here, and only simply transport block would be extracted, and the transport block would be sent to the MAC layers, the receiving MAC layer. So physical layer is converting the received radio signal based on the radio resources that are allocated. It converts it into a transport block, and of course it validates the transport block. It validates the transport block is accurately received, or any CRC errors are there present inside it. It kind of validates that. So after receiving this transport block, what MAC layer is supposed to do? It will have to perform a mechanism called as demultiplexing. What is the meaning of multiplexing? Taking the data from several RLC entities, several RLC PDUs, putting them together, we call it as multiplexing. Demultiplexing is the opposite activity. In the demultiplexing, the receiving MAC layer will read the MAC layer level headers, subheaders, find out in the received transport block, the data belongs to how many AMRLC entities or how many logical channels. If MAC found out that, sorry, there is a mistake. Okay, I will put here. So if MAC found out that there is a data that is present for this first RLC entity, the data would be sent to this RLC. You could have received multiple of them. So you would be sending them to the receiving RLC blocks. I hope you are observing the difference here. We are starting with the reception, the opposite direction. So the received radio signal got converted into transport block. MAC layer is demultiplexing the transport block, dividing the data into several logical channel data. If we are taking the example that we have received the data for each one of the logical channel that is operational, that means if you just to do the opposite, GNode B in the downlink direction might have taken the data from several RLCs, packed them together and multiplexed it. So GNode B is multiplexing into a transport block and sending it to you. When you receive it, when mobile receives that multiplexed transport block, from the multiplexed transport block, MAC layer is segregating each RLC's traffic, each logical channels related traffic. You're segregating it, you're separating that, and on the basis of headers. So each RLC entity received, so they will start doing the processing. Um, First, AMRLCs. AMRLCs will have to perform the routing operation. What is this routing here? They have to kind of find out in the received PDU, RLC PDU, whether the RLC PDU received is a data PDU or control PDU. If it is a control PDU, we learned that this routing entity will forward that status report to the control unit, RLC control block. If it is carrying status report, if it is not carrying the user data, you have received a PDU. That PDU could be either control information or it could be user data that belongs to higher layers. Based on it, the routing will take place. It goes to the RLC control. But I'm not telling you that it is mandatory. Either it could be this direction or if it could be this direction. So this routing will be done on the basis of something called as a device bit, data or control. If the value is 1, it would be put into reception buffer. If the in the device bit in the RLC level is 1, if it is 0, it would be sent to RLC control. So each of these AMRLC entities will have to do that job because their PDUs could be control PDUs or their PDUs could be data PDUs. So if they received data PDUs, by considering that they have received the data PDUs, each of them will be sending it to reception buffers. But in some example, they could also send it to control. You have to imagine that. But in this example, I'm continuing it with the data part. Okay. After the data is placed in reception buffer in all the AMRLCs, everybody have to perform RLC header removals whenever the time is up for reassembly, when the reassembly timer is expired. So we individually studied that. For UMRLC, there is a timer configured, AMRLC, there is a timer configured, reassembly timers, how it operates. But once that expires, they will perform the reassembly. And if it is received in terms of multiple segments or whatever, so we will combine them. But in this example, we are not considering multiple segments and everything. Maybe we are assuming everybody is getting one full PDU at a time. So reassembly operation is kind of not needed. This you can send directly up. So each AM RLC entity, after performing their respective reassembly operations, they will forward their SDUs, whatever that they have extracted. So that would be sent to their respective PDCPs. Okay, there is a question. Abhimanyu. UM and AMRLC segmented data can be retrieved in the same packet. Actually, it is not. Maybe if that is what is the point I told you, because we are considering only one time what is happening. I kind of considered that we are receiving a full SDU in it. It is not segmented. That is the thing that but if it is segmented, you have to wait for the next TTA. In the next TTA, you will receive next transport block. In the next transport block, you will be receiving the next segment, next SDU segment. So that time you have to perform the reassembly operation. Understood, Abhimanyu? But because we are studying only one TTA specific operation here, I kind of wanted to show you this entire process. So I cannot consider that one guy is receiving, for example, only a segment. If a guy is receiving only a segment, it will have to wait for the further segments in the further TTAs, which are going to arrive in further transport blocks. Once the entire all the segments are received, only then you can perform the reassembly and send the SDU to the higher layer. You got it?
Yes, sir.
Okay. So they all of these RLC entities, they deliver the data to their respective PDCPs. So what does the PDCPs do now? The first activity is for them to remove the headers, each one of them. Then they decipher the traffic. Then whatever the message that they have received by using the deciphering algorithm, by using the keys. Then integrity validation, MACI will be validated. And individually, every PDCP will do its own validation. There are 4 messages, 4 PDCPs operational in this example. Now, you put them into reception buffer at PDCP level, and you have to require to reorder and duplicate detection. We discussed those scenarios when it will happen, etc. So PDCP will have to kind of avoid those duplicates. If any for any packets, the duplicates are received. Now, after that, if it is the signaling messages, after reordering and duplicate detection job is completed, you kind of have to send it. Uh, these PDCP entities will directly send it to their RRC. These messages would be sent to RRC, signaling messages. Whereas, if it is for the user plane, operation is little different. Uh, you have header compression enabled on the G node B, for example, for the downlink traffic. So if the headers are compressed in the headers are compressed at G node B, we have to perform the decompression operation. And we already learned why the decompression takes place only after reordering and duplicate detection. Because decompression works based on the sequential packets. So you have to first put them in the order before you perform the decompression. So that's why they are waiting till the things are ordered. So after ordering, so these user plane entities only for which we have this decompression mechanism. So decompression is taking place. So those boxes are missing here in PDCP control control plane PDCP entities, are the SRB PDCPs, we can call them as.
Sir, one question here.
Yeah.
In PDCP like there is no hard process here. So like how we are getting duplicate like data? Like once we are sending, if it is sent, it's sent. I mean, it's
We have
not
seen that
received. It
scenario,
is
no,
like dropped.
Abhimanyu? Remember the
But sir,
handover scenarios we studied?
yes, yes, sir.
PDCP level, for 2 classes, we have studied that. Okay, so when there is no status report at RLC level, there can be a duplicate because the same data will be repeated after the handover also. You understand? Do you remember that?
Yeah, yes, sir. Yeah.
Yeah.
But
So
in
that's
this
that.
case, I don't think this will
In
happen.
this
Like
case, it may not be there. See, in the example, I have to put the boxes, so I have to keep the boxes. So in this case, it may not be the scenario, but the examples I have already discussed for it, when it will happen, etc. In this case, they may not be. Simply the box is there, which may be doing nothing. Okay.
okay, sir.
Okay. So yeah. So header decompression would take place. After that, the original SDUs would be extracted. Control plane messages would be directly given to signaling protocol by these PDCP softwares. And the PDCP softwares operating for user plane, they kind of give this to SDAP. So SDAP will have to look for its own headers in the downlink packets, and it will have to look for the reflective quality of service because RDA and RQA bits would be present. So it will have to see if the RBA and RQA bits are present or not. If they are set to 00, there is nothing that SDAP need to do related to these particular DRBs or QoS flows. Its activity is dummy. But if RDA bit is set to 1, RQA bit is set to 1, then SDAP need to go and communicate with the NAS layer and provide the that quality of service. Your QoS flow mapping rules have been changed, and now there is a reflective quality of service is in force. It'll report it to NAS, especially when the RQA bit is set to 1. When RDA bit is set to 1, if this particular data in the uplink, if you are using a different radio bearer for sending it, you have to stop using that radio bearer and you have to start using the same radio bearer on which you are receiving the traffic. We learned those conditions and rules yesterday in SDAP. So it will apply that rules and regulations here at SDAP. And it removes SDAP header because it is responsible for. So how many number of PDCPs may be there? It doesn't matter. That's the traffic of the after once the SDUs are extracted, they would be sent to the single SDAP, the single SDAP that is working for your PDU session. It's only one. And from there, once you remove the SDAP headers, what you will get out is IP packets. You will extract the IP packets and send them to the corresponding applications. IP packets would be sent to IP protocol layer. It look into IP addresses and then sent to transport layers, look into port numbers. Port numbers will define the data should be sent to which application. When there are multiple applications located in your mobile like WhatsApp, Facebook, etc. Based on those port numbers, you will recognize which data need to be sent to which app. This is in downlink case. Downlink case starts from the bottom, from the radio signal point onwards. You receive the radio signal and send everything up. Is this clear? Any questions in this part? So have you understood the overall L2, L1 aspects here? So whatever we have studied so far in L2, L1 all these days, now this particular slide is a combination or amalgamation of all those things basically. So putting it together at one place from the software point of view. Great. If you don't have any questions, I'm moving out of this slide. Okay. Uh, we already have learned this at the starting of the physical layer, that RRC is kind of responsible for configuring a lot of parameters and different open parameters, which we call it as. Every software will contain open parameters or variables whose values can be decided by somebody. So RRC kind of decides it. We also learned that which RRC decides it is GNodeBees RRC decides most of the parameter values that the lower layers have to operate on. And it kind of provides that configuration details to these layers. First, the configuration would be done on the um, GNodeB, and then the same information would be sent from the GNodeB to the UE. GNodeB's RRC would send it to the UE, and UE's RRC, by receiving that configuration details, it will go and speak to the lower layers and configure the same way that how the GNodeB side protocol stack is operating. The reciprocating manner or the counterpart manner, these protocol layers would be configured on the UE side as well. But uh, we have discussed about one important point here, if you remember. To send the RRC messages, we need to kind of use the lower layers. I have asked this question at that time also. Hey, if RRC is the one who is configuring the lower layers, how the lower layer should work, if RRC is the one that is configuring, before RRC sending this information to UE, UE cannot configure its lower layers. If UE cannot configure its lower layers, how can you send this RRC message by using the lower layers? I have asked this question. You remember that question? Can anyone answer that question now?
So, hello.
Yeah.
So first of all, UE lower layers of RRC, they all are used by default configurations, and
Yeah,
after that they are
exactly.
using.
That's perfect answer. So normally, before RRC sends any configuration details to the UE, lower layers have to function even to carry the RRC message, because RRC message also going through the same layers. So what kind of configuration they will use? For that, we have to use a default configuration. Normally, default configuration is applicable when we are operational with the common channels. We call it as common logical channels, common radio bearers, etc. So we use common configurations. So by using common configuration, first time we would be able to send the message even by using the lower layers. But once the message is sent, now you can provide dedicated configuration to the from GNodeB's RRC to the UE's RRC. Now, this RRC and configuring the lower layers, how this whole mechanism work together. So we have to kind of study that in a very high level picture. So this particular thing that we are going to study kind of give us the software level, the software design level mechanism. So how to design the software and how these protocols will internally work and create the things needed. Okay, you see one line here in the middle of the slide. So on the left hand side, we have the UE. On the right hand side, we are going to have the GNodeB. Now these are the protocol layers, softwares that are present. Now the C represents kind of common software. Common software typically works with common channels. That's the kind of idea there. Now, normally when a GNodeB is configured by operator, GNodeB can send several types of data to the mobile, like system information called as MIB, SIB1 or other system information blocks, or incoming call related advertisements called as paging messages. Or if mobile would like to communicate with some kind of a signaling with the GNodeB should be ready for that. So all these general things would be dealt by this RRCC, which is, you can consider it is a small piece of a RRC software which is doing common things related to every subscriber that is present in the cell. You can kind of consider that at this particular stage. Now, if GNodeB would like to send these data, MIB, SIB1, SIBs, paging or signaling, what is the kind of configuration it will have to use for the lower layers, PDCP, RLC, MAC and physical layer? Default configuration. That is the default configuration that you are seeing here. So for MIB, SIB1, SIBs, paging, etc., you don't have PDCP present because PDCP won't be working along with the RLC TM mode. For all these kinds of data that I have put here, RLC is definitely working in TM mode because most of these things are before RRC connection is established. So RLC is operating in TM mode. And for most of the things where RLC is working in TM mode, MAC is also working in transparent mode. MAC transparent mode means MAC won't add any header. Like for example, we have studied that BCCH to BCH mapping or PCCH to PCH or BCCH to downlink ACH. So those kind of things, MAC won't attach the header. Whenever header is not attached, we kind of call that MAC as transparent MAC. So RLC is transparent, PDCP won't even be there. It won't even be functional for SRB0 to carry signaling messages from the mobile or to receive the signaling messages from the mobile. Now at physical layer, these informations, where do they, how do they get scheduled for the mobile? For example, MIB, it can go on SSB block, SS block, synchronization signal block. And remaining things, SIB1, SIBs, etc., they would be scheduled by using SIRNTA and PDSCA channel, by using special RNTA reservation. Paging messages would be sent on PRNTA reservation. And if you are sending signaling messages on SRB0, they would either be going on a RERNTA or temporary CRNTA during random access procedure part. Because most of the time SRB0 is involved along with the random access part. So you either use RERNTA while receiving the random access response or temporary CRNTA for message 4 in your random access response, one of the two. So what physical layer resources we use to transmit to what data, and what is the default configuration that is applicable for each layer here. It's kind of standardized. And this standardized configuration is known to both G-Node-B as well as every 5G mobile in the world knows this configuration. This is how these layers work, at least to start with. So if a mobile equipment is coming up for the first time in the network, definitely in the mobile also all these protocol layers would be there working. Now, the first task for the mobile is to get the MIB, master information block, the crucial system information from the system SS block. Now, mobile knows the configuration it will have to use for the lower layers, how the lower layers must operate when I am receiving this SSB block. So I will be getting this SSB block on a special physical resource, which can be identified with PSS SSS. Mobile knows that, how to detect PSS SSS, where to download the SSB, it knows, and in which layer, which way MAC is working. MAC doesn't need to remove any header when you receive the SS block, because what you receive here is a BCH. From BCH, if you receive, you don't need to remove any header, without which directly you can send the data to RLC. RLC also is kind of working in transparent mode, no header. Simply the data would be sent to RRC. So if the data is going on these logical channels and physical channels, this is how. So this whole picture is telling you how mobile is receiving its MIB, working and operational on what channels, put together, all the layers together. Earlier we have studied what happens in each and every layer. Now we are combining everything into one single picture. So mobile will detect the SSB block. In that it will separate or segregate the PBCH resource elements. From that it will extract one transport block which is named as BCH. When it is presented to MAC layer, UE's MAC layer as BCH, UE's MAC layer knows that for BCH transport block there won't be any header. So it is transparent. You directly send whatever you have received to the RLC. RLC also knows that it is operating in TM mode, no header. The data would be directly forwarded towards RRC. RRC receives that MIB, the digital information, it will convert it into master information block. PDCP won't be there, not involved as part of this default configuration. Are you getting it, guys? Are you getting this clearly? Now I'm combining everything, logical channels, transport, physical, the total configuration operation of the lower layers. So far, RRC is not configuring anything. Of course, we have to study RRC very deeply, like how it will configure the lower layers in different situations. But before that, what happens at the starting with the aspects that we have discussed so far? Okay, next. Our mobile equipment software also knows that, hey, if it wanted to receive any further, if it wanted to receive SIB1, SIB1 arrives by scheduling against SIRNTI. Mobile knows that. And SIRNTI is a fixed number. It will be looking onto this PDCCA channel, which resources are reserved against SIRNTI. And MAC, default configuration, RLC default configuration, PDCP default configuration. So you wait for the correct time and download that on PDSCH whenever it is scheduled. But on SIB1, mobile will get clarity whether the rest of the SIBs are going to come to him either in a scheduled fashion or whether they are going to be broadcasted. So we have a on-demand system information mechanism that is applicable in 5G. What is that on-demand SIB and etc. I will tell you later. But first things first, I hope you got this point. You remember this point. The system information, whatever is available for the mobile, is the crucial system data that is required for every mobile to survive in a cell. That is divided into MIB SIBs. MIB system information block 1, system information blocks. There are up to 24 system information blocks in release 17. Of course, in next release, they might add some more system information blocks. These are required for crucial operations for the mobile in the cell, crucial details that the network wanted to advertise for every UE. So now, based on some information that the SIB, we have received in SIB1, you can already see that RRC is going and telling something to the physical layer. It might be telling the physical layer that, hey, you know what? If you wanted to download the remaining SIBs, they are going to arrive in so-and-so position. It kind of convey the details to the physical layer. In case it is not on-demand SIB, if it is a scheduled SIB, that means the SIBs are getting repeated continuously every now and then, like with a predetermined interval. That aspects of on-demand SIB and scheduled SIBs, I will explain it in the tomorrow's class when we go deeper into it. But what is this yellow arrow? You have to understand it. RRC based on the SIB1 information. So it got some configuration details in SIB1. It is telling to the physical layer that, hey, if you wanted to download the remaining SIBs, you have to look for the PDSCH channel or PDCCH channel in so-and-so position, in so-and-so time. It will giving the timing information with this arrow. So now you can already start understanding how RRC is kind of controlling the physical layer and telling physical layer what to do, when to do, in a particular aspect from one particular point of view. Like in this particular case, to receive the SIBs, what it is supposed to do, it is clearly giving those instructions. UIS RRC is giving that instructions to UIS physical based on the information you received in SIB1. So when we introduce these SIBs tomorrow, so definitely we have to look for, hey, what information that we have received in SIB, which is kind of giving this GAN to physical layer about the remaining SIBs when they arrive. That we look for it. Or I'm giving you a hint that we have to look for it in that information tomorrow if we introduce that SIB. So now it got the scheduling details related to the remaining SIBs. So physical layer is happy. It is ready to listen to PDCCH channel, PDSCH, etc. to download the remaining SIBs that are arriving, that are required for your operation. Based on this configuration provided from SIB1. Remaining layers, MAC, RLC, and PDCP is default configuration. MAC transparent, RLC TM, PDCP won't be there. Wait for the exact time unit when the SIBs are going to arrive. You download that. Genode is sending it, mobile is downloading that on PDSCH with the SARNTA reservation on PDCCH channel. Reservation details happen on PDCCH, but the actual data arrives on PDSCH. From the downlink SCH, you would extract BCCH, MAC, but it is still transparent. No header will be added in MAC. Now these SIBs will give a lot of configuration details actually related to the cell and how mobile equipment should survive in this particular cell. Lot of details. Different SIBs will carry different details, which we elaborate in our coming up sessions. What SIBs will carry what data. But because we have to understand about this paging or incoming calls, these SIBs will kind of carry something, some mechanism, some information related to paging, or when you will be getting your paging messages. That is possible. It is configurable. So again, we are telling the physical layer, we are giving GAN to physical layer. If you wanted to download the paging information on the PRNTA reservation, where you have to look for. So then mobile would be looking for that. If at all it is listening for incoming calls, if at all it will have to listen for incoming calls. So it will be able to download that even for that default configuration. Because these are all common channels. PCCH to PCH sent on PDSCH with PRNTA reservation. Now these are all downlink channels, as you can observe with the arrows, network to the mobile, not from mobile to the network. All of these are downlink, network to the mobile. Now we have to study mobile. For example, it wanted to make a radio connection, RRC connection. Now it need to communicate with G node B. It need to send a signaling message to the G node B. So for the first time, mobile is preparing a signaling message. But for sending a signaling message, mobile will have to use something called as SRB0 configuration. But SRB0 configuration also must be default configuration. You cannot have a dedicated configuration because mobile never spoke to G node B so far. This is the first time mobile in fact wanted to speak to G node B. So definitely we'll have to use default configuration. No PDCP, RLC operating in TM mode. Mac kind of does the multiplexing and demultiplexing. We kind of call that as CCCH getting multiplexed onto uplink SCH. For that logical channel number is 0. We have learned that already in the Mac layer level. And which resources you have to use to schedule, to send this prepared signaling message, either the resources that are allocated against your RA-RNTA as part of the RAR, as part of your random access procedure. By using those resources, you will be sending your first signaling message, which we have named as message 3. So message 3, CCCH to uplink SCH, sent on PUSCH resources that are acquired by using your random access procedure. Of course, I did not include that random access procedure related thing in this because I could not draw it here because the space is not enough. So I have kind of ignored it. So we are considering that when the signaling message need to be sent, when it arrives at the TM RLC TM block, RLC TM block will talk to Mac layer, tells that, hey, I have a message waiting, please send it. Because mobile is in idle mode, we know that Mac layer will trigger the random access procedure by sending a preamble. So it will have that ratch and everything, but I did not include that ratch part here. I kind of ignored because we have studied that anyway extensively. But you have to kind of imagine that that is already occurred as part of this procedure. So by using the resources you have acquired by using the random access procedure only, in that only you get your PUSCH resources. You are preparing uplink SCH transport by packing CCCH with logical channel ID number 0. You are sending it uplink, and which G node B receives and receives that RRC connection request. Now from here onwards, the special thing will happen. Once mobile receives that connection request or RRC setup request, it's called as RRC setup request. Once it receives that message, G node B's RRC will start the next activity. Says that, oh, one particular mobile came to me, sent me a message called as RRC setup. It would like to have its own dedicated configuration. It is fed up of using this common configuration that is working right now or a default configuration that is working right now. We have to use some specific configuration for this guy. It is demanding for that connection. G node B understands it. So what does the G node B do in the next step? It decides to accept that. So we are taking a positive case. This RRCC software will create a special RRC D entity, RRC dedicated entity, which is, you can kind of, if you take object oriented programming, it's kind of, you can consider that that is a separate object getting created in your software for the subscriber. For one subscriber, how many RRC Ds would be present? Can be many, dedicated, one for one subscriber. The responsibility of that RRC-D is to deal with only this subscriber from now onwards. This is software design at various protocol levels. So it is kind of self-creating one entity and telling him that from now onwards, because mobile is coming into connected state, if mobile wanted to speak to you, you deal with it. I won't be dealing with it. RRCC telling to RRCD. Why? Because as a RRCC, my duty is to only keep distributing common information. So you kind of can design it. Of course, it need not be same in every protocol stack developed by every company, guys. I'm telling you general process that is followed by the companies. In different companies, the design will be different for protocols. Protocol internal design is not standardized by 3GPP. This is something that I'm visualizing, I'm presenting it to you that this is how it could be done in a software. The software level implementation details won't be told by 3GPP. Okay, so what does this RRC do? Now, this RRCD creates a special PDCP, special RLC, special MAC entities. Says that, hey, from now onwards, mobile, when it is communicating with us with signaling messages, we kind of have to use some dedicated configuration that is applicable for the mobile only um, with in the connected state. So we should not let mobile use the default configuration that it is using for common channels. Some separate software entities have been created for each subscriber. So GNODB software is getting the divisional architecture here. For each UE, it is creating separate instance at every protocol layer. And those instances can have sub-instances inside when you are designing. Okay, now, first, what does the GNODB do is, it knows that it need to send some signaling messages and receive signaling messages from the mobile. Once the mobile is uh, into the connected state, so it kind of creates the required configuration. So it creates configuration for SRB1. This SRB1 comes into the play once the mobile equipment is in connected state, not in idle state, but in connected state. So this SRB1. So the corresponding configuration would be done in the PDCP, RLC, and MAC. Entities would be created. PDCP control signaling entity, RLC working in AM mode. MAC layer is having the multiplexing, demultiplexing mechanism and logical channel prioritization, etc. Those details would be sent to MAC layer. And the scheduling would be done for sending or receiving the data on this SRB1 against CRNT reservation. So every layer is prepared. So SRB1 specific configuration is done on the network first. Okay, now I have asked you one question. You guys have to tell me the answer. I desperately expecting an answer from you. So you have to be involved. Listen to the question carefully. SRB1 configuration is already present here, as you can see. Now, my question is, can GNODB start using this SRB1 and send the data to the mobile? Yes or no? Simple answer. If RRC wanted to send any signaling messages, GNODB's RRC want to send any signaling messages, can it to send those signaling messages to the mobile, can it use this SRB1 configuration or not? A simple question. Yes or no? Participate, guys. Anyone? Simple answer only, no? At least you can throw a stone. Somebody told no. Okay. Any other answers? Two no's.
To say, at least actually yes or no say.
Yeah, sorry. Can you repeat?
No, I'm not asking you. Probably I'm just telling guys to just respond.
Yeah. No. A lot of you people are saying no. Okay, that's a good thing that you are at least saying correct answer. That is no. But why do you guys think it is a no? Why do you think this configuration, this SRB1 configuration cannot be, like, won't be used by GNODB to send the signaling message now? For example, mobile sent RRC connection, RRC setup request. It is requesting for a radio connection. We need to respond back to that. That is called as a reply message. Now, can you send that reply message on this SRB1? Because it's already configured on the GNODB side. All of you are telling no. But why? Why it can't be used? Because it's already configured on the GNODB. It is actually, answer is in front of you. The configuration is not known to the mobile equipment yet. Because UE side protocol stack is not aware of that specific details of that configuration, SRB1 specific related details. So If network blindly uses that SRB1 configuration and sends any message, mobile failed to decode that because the headers and everything would be dependent on that configuration. Sometimes header field sizes also would be dependent on the configuration. So mobile don't have any idea about it. So when we are sending the first message, RRC connection, RRC setup request, whatever the response that network is sending back to you, that response should come by using SRB0 itself. It cannot come on SRB1, even though it is the configuration is done on the network side. It must use SRB0 for response thing. So first GNodeB completes this configuration. RRCD will go and talk to RRCC, tells that, hey, I have done my job, I'm ready. If mobile comes to me, I'm ready to take up the activity. And I will be using SRB1 once mobile start using it. So this is the SRB1 configuration I'm providing you the details. So the details would be sent to RRCC, which will kind of pack it into a signaling message, a reply signaling message. That reply signaling message will follow the same path. Now you can observe these arrows will be reappearing once again, this SRB0 part. You observe that animation. It would be sent from CCCH to downlink SCH on PDSCH. It will arrive on downlink SCH, CCCH, SRB0, RRC received that signaling message. Once mobile received that special configuration, SRB1 may contain some special configuration details. And once this RRC gets the configuration details, it go and talk to individually to each of these protocol layers. So it will create that required configuration in every layer by speaking to them. So it will create that SRB1, same configuration, whatever that is existing on the mobile, the reciprocating configuration. Now mobile, if for example, if this particular procedure need to be continued further, now mobile can definitely use SRB1 as it is already present on the network side. So mobile can use SRB1. It doesn't require to use SRB0 anymore. SRB0 is kind of in before your connection establishment is done. But now it is done. You can start using SRB1 for signaling messages that you would like to send. So NAS may give a message, signaling message to RRC. We have learned that NAS messages would be packed into RRC. So RRC kind of packs the NAS message inside. But to carry that NAS message, we can now use SRB1 configuration. And if we send it uh, by using this DCCH mapped down to uplink SCH, by using the continuous resources that you are getting in uplink PUSCH, it would be sent to the mobile's RRCD signaling entity. NAS message would be extracted and it would get forwarded towards the AMF because GNodeB is not responsible for dealing with the NAS message. But if there is any meaningful RRC information present inside it, actually when NAS sends the NAS message, RRC also can pack some meaningful information. So there can be two things, NAS plus RRC. But once we send here, so the RRC will read only its part, RRC level information. NAS, it will kind of remove it out, send it towards the AMF by using a separate protocol stack, which we have already introduced, like the NGAP protocol stack. It will use to start sending it towards the AMF. Now, this communication, now actually speaking, mobile equipment's NAS and AMF's NAS layer will talk to each other for a lot of time. Like AMF will authenticate the subscriber, challenges the subscriber to prove himself, etc., etc. Lot of activity will happen at the NAS level. Any of the NAS messages that are happening either in uplink direction or in downlink direction, they will be going through these SRBs. For example, if AMF sends any NAS message to GNodeB, GNodeB packs that into this RRC SRB1 right now. and it can kind of send it in downlink SCH transport block, PDSCH reservation, and the message will be received here, and it would be sent to NAS layer. So a message arrived from AMF to AMF's NAS software to mobile equipment's NAS software in the downlink direction. So the kind of this SRB1 is kind of now functional, and mobile equipment is said to be in connected state, working with a dedicated configuration provided by the Gnode B. It is not using the common or default configuration. It may be still using some default parameters, but not, there can be some dedicated parameters also suggested by Gnode B to the mobile at the lower level protocol layers. But so far, only signaling is taking place. But at one point in time, user data also should come into the play. DRB need to be created, user data need to come into the play as well. There are some rules and regulations when you can create the DRB. There is some rule called as only after enabling the security mode at the PDCP level, you can you can create the DRB. Those rules I will talk about later, but we are going to kind of assume that now it is the time for creating the DRB, for example. Now, I have a question. If at all we have to create a DRB, right now whatever we have is a SRB, that too SRB1, which mobile is using. Now my question is, if a DRB need to be created, please tell me, DRB will be created first on the Gnode B side or mobile equipment side? GRB configuration will be created. Radio bearer configuration means configuring all the lower layers and their working style or their working modes and their operational mechanisms. Configuring that is what we call as radio bearer configuration. Now my question is, if DRB need to be configured, will it first be configured on the Gnode B side or on the mobile side? What you believe is correct? Answers, come on, participate. Okay. So a lot of you guys are telling Gnode B. Good. Can you please tell me if Gnode B need to configure the DRB, to configure it, what it will take as the basis? Yesterday we studied as part of the QoS infrastructure. Can you tell me how Gnode B will base its DRB configurations? Exactly. By using the quality of service profile that is arriving from the SMF. We learned that as part of the QoS infrastructure. So by using that QoS profile, Gnode B would be able to configure the DRBs on its side. First, it will be configured on the Gnode B side. The same thing will be replicated on the mobile by providing the details. So now that activity will take place. But there is also a concept of SRB2, which is called as low prioritized SRB compared with SRB1. So SRB2 also will be created. That means for sending the an appropriate time. What is that appropriate time and when it will be done? I will explain those things when we are going deep into the RRC. But you require a second radio bearer for signaling, SRB2. You require at least one data radio bearer, at least a default one, DRB1. So first the configuration would be done by RRCD in the lower layers. So PDCP entities and the corresponding RLC MAC physical layer configuration, everything would be done. And you first time you would be creating SDAP also. SDAP is applicable only for DRB part, where you will kind of create the mapping between the QoS flow that you are bringing up and on which radio bearer you are sending. If you are creating only one DRB, SDAP kind of working in no header mode, so you don't require to even note down the QFI part. But that depends on how it is configuring. But first I'm talking about configuring. So network configure these details on its side first. Now I'll ask you another question. Tell me, once network configures these details based on the instructions received from SMF, that is good. But we know that the same configuration need to be repeated on the mobile. Now my question is, by using which SRB these details would be sent to the mobile? That's my question. By using which SRB these SRB2 or DRB configuration details are sent to the mobile? Okay, a lot of you have answered SRB1, that is correct. But one of you have answered SRB2, Deepesh. Why do you think it is SRB2, Deepesh? What is the reason behind SRB2? There is a problem with SRB2 configuration, right? What is the problem? At least someone will tell me why we can't use SRB2 for sending these details to mobile. Because SRB2 is not configured on the mobile. How can we use SRB2? Because we are kind of configuring SRB2 plus DRB1 combinedly here on the network side. Without presenting those details to the mobile, you cannot blindly start using SRB2 and sending the traffic to the mobile. Mobile would be confused. Is demultiplexing, everything will fail because you don't know those logical channel numbers and so on, the header related aspects. So you should not use that SRB2. So you're packing all these details and use SRB1 and send the message to the mobile in downlink SH, transport block, PDSH, you receive that. And now the UE side RRC, once it receives that signaling message and understands it, decodes it, it will do the configuration by talking to these lower layers. Hey, you guys have to come up, start working for my SRB2, and also you guys have to create DRB for the data purposes, for letting the application data go. Each one of you have to work in this particular way. I'm giving you sequence number sizes, reassembly sizes, retransmission sizes, etc., etc. Of course, someone pointed out, Avinash, we can use SRB0 also, you said. Now, SRB0 is using common configuration. Already mobile equipment is moved into connected state. Why do you think we again have to use the common configuration that you are using before RRC connection? Because you already got a dedicated configuration called as SRB1 that is specifically created for your need. Based on your conditions and your situation, network configured that SRB1 for you. SRB0 is kind of for wherever you are in the cell, and it can contain generic details. So you no need to use SRB0 when you are already in connected state and when you are using SRB1. When you don't have SRB1, using SRB0 makes sense because it's common configuration. But after SRB1 is there, you don't require to use SRB0. Okay, because this point is brought up anyway, now I'll ask you one question. Mobile is already in connected state, So SRB1, SRB2, DRB, all of them are configured. But still in some situations, mobile will use SRB0. In which cases? Can anyone tell me? In which cases mobile would use SRB0? Even though SRB1, 2 and DRBs are all present, but still mobile would use SRB0 when? Participate, guys. Only 2 answers received. More participation, please. Better you enable your mic and speak so that others will hear too instead of typing answer. Guys. Because others don't know what you are typing in the chat box. Only I can see that.
Sir, in cases where we have to use check something with different UEs, like different things, which UE is working well or not.
Okay, that is a very generic answer. Kind of
The
did not give
handover case.
handover case. Okay. I will tell you one
RRC configuration.
reconfiguration. Okay. I will tell you one easy thing. Instead of even going into handover, handover is dealing with separate, like Gnode B or separate cell, wherein you will kind of have to start with SRB0. That is the correct thing only. Obviously, you have to do the non-contention based random access procedure in the new cell. You will perform that. But I am kind of asking the question within the cell. You are giving indirect answer that re-establishment, but I want specific answer, which we already have discussed. At the MAC layer level, I have introduced that topic to you. Anyone? Okay. I'll remind you. For example, mobile lost the radio link for some time. You have suddenly entered into a lift while you are using the 5G network services, but the lift is kind of a closed lift and the signal is not going through, radio signal is not going through. Such a situation is what typically we call it as a radio link failure. Once mobile encounters the radio link failure and it comes out of the radio link failure, now, before the radio link failure, mobile is in RRC connected state, happily using SRB1, SRB2 DRBs. But after the radio link failure and come back from the radio link failure, mobile is kind of tentative. Hey, I have come up now again, my radio signal is reinstated. Now I have to speak to the network to find out what's going on. But mobile will start thinking, hey, can I use my SRB1, SRB2 or SRB1 to talk to the Gnode B? Mobile would try to think it's himself internally. Then mobile will kind of get an idea. I don't know how much time I have gone out and how much time my radio link is failed and whether the Gnode B is still keeping my configuration or not, I'm not sure. Maybe Gnode B might have considered that I'm gone for too long and already removed all this dedicated configuration which is created for me. So if I blindly believe that Gnode B kept the configuration and used the SRB1 and SRB2 for communicating with Gnode B may not even be getting those messages or that doesn't work out. Because the same configuration is still not there on the Gnode B. As you are gone for too long, network remove that configuration by detecting your radio link failure. So mobile is not sure whether the SRB1, SRB2, DRB are still there, network still kept them or not kept them. It is in dilemma. So in that dilemma, it cannot take the risk of using SRB1 and SRB2 after coming out of the radio link kind of situations. It would use SRB0. Because it can always use that common configuration. It knows that network listens to it. But when you use SRB0 and send something called as a re-establishment request to the network detects that, oh, this bugger I already know. There is already RRCD still present. It is not deleted. The configuration is not destroyed yet. We are still waiting for the subscriber to come back. Luckily, this guy arrived within the timer expiry, within the re-establishment timer expiry. So we kind of accept this guy. So we put this guy back onto the dedicated configuration, whatever this guy is using earlier. We don't need to start from the scratch. So in such cases, using SRB0 makes sense. But you won't use SRB0 when SRB1 and 2 perfectly working. The configuration is perfectly working and everything is going on perfectly for you in your network. You got that?
Yes, sir.
Okay. So now, how this SRB2 and DRBs would function. So if mobile would like to send any NAS messages, once SRB2 is configured, it kind of have to use SRB2 for sending the NAS messages. And they can be packed inside RRC as well. But if you have any user data, IP packets, come to SDAP, which will map onto the DRB if the configuration is existing. So ultimately, I'm showing you the concept. So DTCH or DCCH mapped onto uplink SCH sent on PUSCH resources. And if that is containing any NAS messages, they would be sent towards the AMF. Data that is extracted out of your SDAP would be going towards the UPF. Or vice versa. The arrows are directional. So I can show you the downlink also. When the traffic is incoming from the other side, is either the NAS messages or the user data, they would come in downlink by following similar kind of an arrangement, and it would be sent to the corresponding entities. Is this clear, guys? Is this design part clear? Understood?
Yes, sir.
Okay. So in our next class, what do we do is how exactly RRC does this? What are the different RRC messages RRC sends in different situations? And what is the contents inside it? And the deeper details. We'll go for that in our actual RRC session. So this is a kind of intro for our RRC. Okay. Any questions?
Hi, sir. So just for
Yeah.
curiosity, I want to ask one question. Can a 5G UE act as a G node B and share its resource to other UE?
Can a 5G UE?
Can act as a G node B and share its resources to other UE?
It can in IAB scenarios. It can. It is kind of creating a hub in IAB. But IAB is not part of our curriculum. I did not put that thing in there. But it is possible. Mobile can act as the a G node B. For towards other mobiles, it lacked as a G node B. Towards the G node B, it lacked as a mobile. We have studied that in the MAC, in the buffer status reports. I have explained that concept a little bit. So we have special buffer status reports for IAB entities where you will be reporting the logical channel group data buffers for up to 256 groups, especially for IAB parts. We called them as extended buffer status reports. Okay, but normal mobiles won't use those patterns. But that is possible.
Okay, sir.
I would provide. I did not get time because we took a vacation break in the middle to correct the last two test related things. So anyway, tomorrow we don't have session. Sunday, so I will get the time to correct your test results, and also I will send you the answer sheets for that test part. So today I will send you the answer things for the previous two tests, and I will send you the score that you have sent to your management after I correcting them. But yes, I will send them today for you. Rahul, any other questions? Okay, we will have the test on the quality QoS arc frame structure that we have studied in our previous classes, and also the questions will be from the GTPU, SDAP, and also from the PDU user plane protocol. So all of it, you please prepare in the weekend, and we take up the test on Monday, and please prepare for that. I have already shared the material yesterday night. I hope you have received it. Okay. Any questions? Anyone else? Great. If we don't have any more questions, we'll stop here for today. When we come back, we continue with this RRC into its deeper aspects. Okay. Thanks, guys. Have a nice
Thank you,
weekend.
sir.
So
Thank you,
let's
sir.
come back on Monday and continue.
Thank you,
Thank
sir.
you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you.